All right, good evening. Hopefully everybody can hear me okay. Excellent. All right, so assignment 2 is due. I've heard from a couple of people that they had a couple of last minute things that they were working through, so please continue doing that and get assignment 2 in. Hopefully everybody was successful and get those turned in. I haven't checked Blackboard yet to see how those were looking. So do we have any questions before we get started? Touch and go, but at least it's done. Yeah, it was a big assignment. There was a lot of complexity to it. Hopefully, you were managing your time and you were making progress the whole time and weren't just leaving things towards the end. I'm hoping that's what was going on because there was a lot in the assignment to do, and the whole idea was giving you some introduction rather to some software design processes to hopefully help you set up a plan and execute like that. The assignment number 3, I'm going to post on Wednesday. And for the quiz, yeah, we talked about that. I said either Wednesday or Monday. And right now, I am pretty sure I'm doing it on Monday, not Wednesday. As a matter of fact, I just decided it will be next Monday, not Wednesday. That's good to hear. No, assignment number 3 will not even be close in complexity. The idea is it's going to be a straightforward assignment that you can do in a 2-week period. It's going to be different because it's going to be using some tools that you're not familiar with, you haven't used yet. So that's going to be the real complexity about this, is actually digging in to, well, might as well go ahead and mention right now that it's going to be based upon the Lex and Yak tools. So if you want to start getting familiarity with Lex and Yak, or Flex and Bison, I would recommend over Lex and Yak. I would start doing that and become familiar with it. And that's what we will use here for assignment number 3. As far as whether it's individual or paired, it's probably going to be individual. It's where I am leaning right now, because that's the only way I can really tell if you've learned how to at least get through doing some very basic Lex and Yak capabilities. Okay, any other questions? All right. Then let's go ahead and change over to where we had left off. At least, let me see. Yeah. Change screens here. Go over here to the PowerPoint. And this is where we had left off. Okay, so we took a look at using the bottom up approach in parsing, and now we're going to take a look at top down approach in parsing. Okay, so the top down approach is a recursive descent parser. Now, instead of using an LR grammar, we're going to use an LL grammar. That would be left to right, leftmost derivation. Okay, and what we're going to do is, instead of using a stack to help us evaluate each of our statements using these grammars, we're going to use a tree to evaluate it instead, which kind of makes sense, right? Because In a tree, you're going to go left to right, and you're going to go down, top to down, and then you're going to start coming up and keep going back down and then keep coming up until you've completed reading all of your statement or all of your inputs. And then you can evaluate. Okay, that's why we're going to use a tree. Okay, really high level, but we'll take a look at some walkthroughs here to help visualize it a little bit better and understand it better. So the recursive descent parser is going to be based upon rules. We'll express those rules in BNF just like we did in the previous grammars. And we're going to evaluate each of the tokens and building the tree from the tokens. So all of that is just like what we were looking at with the bottom-up parser, except we're going to use a top-down approach and trees instead. So what we'll do is the parser will then call the rules procedure, which is then going to read the tokens until it can make a match. And it's going to make a match just like we were doing with the bottom-up approach, using a substring, as large a substring as we can, that we can recognize and classify those tokens as. Okay, and the tokens will be the same type of thing we were looking at before. They could be terminal symbols, keywords, reserve words, operators, IDs, same type of thing that we were looking at with the bottom-up approach. Okay, so having said that, then like we had seen in the previous parsers, we can call a rule, or we can call another rules procedure, or we can even call our rule recursively, depending upon how that rule was defined and what we're reading, of course, and if it matches that rule's definition or not. So we could do all of those things. All of that is the same thing. We're just using this different approach. And so what we'll do is we're also going to be concerned with the level in the tree. Now, with the stack, it wasn't so much that we need to keep track of the level, because as you recall, and just like you recall from stack structures anyway, that you're pushing and you're popping from the stack, and really the only thing you care about is the top of the stack, which you know, and then a null stack. Those were really the only things that you cared about. But when we're doing our top-down parsing, we are going to care about the levels, because like you're traversing any other tree, if you're traversing a tree from left to right, then you can go up and you can go back down on another branch. And you come back up and you go back down on another branch. And if you're concerned about the levels that you're going down, then you can track that as well. So that's one thing that's a little bit different using the tree structure than the stack structure, but that's just like you've been working with any other tree or any other stack previously. All right, so nothing should be nothing new there. Basic stacks and basic trees, right? So we're going to use the same type of basic operators with trees that we saw that we use with stacks. Okay, but now let's take a look at our grammar. And this time we're going to take a look so we can understand a grammar for a specific solution that we can use then as our example to help us understand how we could do this top-down approach using an LL grammar and trees to manage it with. So in this case, the Pascal grammar, just like we saw before, but now you'll notice it's a little bit different. Okay, sure, come back to me. Sure, the most top level rule that we have for the program, the prog, is to, let me put my little pointer to a bigger pointer so you can see it. There we go. So the program or the prog is defined to be program reserve word followed by the rule prog name followed by the reserve word var followed by the rule deck list followed by the reserve word begin followed by the rule statement list followed by the reserve word in followed by the period. Okay, so that's just like we saw before. And the most fundamental rule, which is the body is defined to be a rule statement, or it could be the reserve word begin followed by a rule statement list followed by the reserve word end, no period. Okay, just like we saw that before. And then all of these rules are the same, but you'll notice I highlighted in red some rules that are different using this top-down approach than the rules that we saw in the bottom up approach. And remember, a couple of those rules were defining the order of precedence for processing. Okay, so let's take a look at that. Okay, we come up to a basic term. Okay, so a rule term, is defined to be a factor followed by, it could be either a multiply factor or a div factor. Okay. Now notice we wrote this a little bit differently than we did in the bottom up approach, right? Here we're using the eBNF format, as you probably recall, right? So it's, since we didn't have any special operators over here, what we're saying is that we could have 0, 1, or many instances of what's inside the curly brackets. So we could have a factor all by itself be classified as a term. Or we could have a factor followed by a multiply factor that can classify as a term. Or we could have a factor followed by a div followed by a factor, and that too could be classified as a term. Then in an expression, we say the rule expression is defined to be a term, and then curly braces, no special symbol here. So it could be classified as a term, can be classified as an expression, or a term followed by a plus followed by a term. It could be expression or a term followed by a minus followed by a term. Can also be an expression. So all of that is the same. All right, it's very similar. I'm just using eBNF to express it, whereas before we used just basic BNF. And so since we're using eBNF, we're going to use eBNF throughout our entire set of rules. It would be bad of us to mix those up, have some of these defined using straight BNF and some of these defined using eBNF. That would be very bad. So we're not going to do that. So what we'll need to do then is we'll need to come up to our statement list, which we used before down here, right? Statement list is defined to be a statement. Again, we have curly braces and no special symbols. So it could be a statement by itself, or it could be a statement, semicolon statement. So that's the statement list. ID list can be a single ID. You have curly braces, no symbol. So it could be a straight ID, or we could have a comma separated list of IDs. So ID, comma, ID. And ID, comma, ID, comma, ID, comma, ID. That's as long as we're following that pairwise operation construct that we defined in here. Likewise, this is a pairwise construct that we defined here that we would also have to conform with. And then the other thing that we changed was our way we defined our rule deck list. So the deck list is defined to be either a deck by itself, or it could be followed by a pair of semicolon deck, and then additional ones and additional ones, because you're only going to classify them a pair at a time. All right, so that's how we're going to redefine the Pascal grammar using our LL technique here with the eBNF as an example of how you could write the specification grammar using eBNF. Okay, so recursive descent parsing then. Let's take a look then at this example here where we have using the Pascal syntax, we have a variable variance is set to some variable sum square, reserved word div, a value, decimal value 100, minus a variable mean times variable mean. Okay, so that's very explicit. I stated it very explicitly like that so we can follow along and understand this. All right, so variance. So what we're doing here is we're doing pairwise operations, as you probably recall. So we have variance followed by an assignment function. All right, so variance itself by itself is nothing. It's a char array, as you probably recall from the first phase of our compiler, where we're just reading in symbols and classifying them. In this case here, we had an ID, right? this fits the definition of an ID. So the first thing we're going to have to do is recognize an ID. So we have these symbols variance, which then gets classified as an ID. So an ID, and we're just going to start serializing them. This is an important step as we follow through here. So we're going to serialize the IDs. So the first ID will be 1 instead of 0. Got it. But we're going to go ahead and start with 1. So variance, we read that, it gets classified as an ID. And then pairwise operations, it gets this colon equals. Well, a colon equals is a reserved word that means assignment operations. So we put the colon equals next. We have the variance, we classified it as an ID. Then we have the colon equals, which is that special symbol, going back to your grammars, your alphabet, right? It's an assignment operator. So now we have a rule, assign, that can say, oh, an assign is followed by an ID followed by this. ID followed by this reserved keyword here, followed by an expression. So if we're going to recognize our ID and our assignment, to recognize an assignment function, we need to recognize now an expression. So an ID was a fundamental component, right? So we're going to start looking for those rules that can accept an ID. And we have an index expression, which is an ID followed by assignment, followed by an expression. So we're going to be worried about this one. We have an ID can be a factor, and then a factor can be followed by other things, but so it's not going to be that. But assignment could be a ID followed by an assign, followed by an expression. And we can also have an ID list, but we're already know we're not following that ID with a comma, so we're going to be looking for another rule that'll accept an assignment. And then we can have an ID by itself, which would be a prog name. But we already know we have an assignment operator, so we really have only 2 rules here that we're going to have to worry about. So what we're going to do is we're going to go ahead and further classify the next thing that we see here, which is going to be these chars, SUMSQ. So SUMSQ, I'm going to come right down here where I'm kind of going backwards a little bit, where we could say SUMSQ can be classified as an ID. And that's what we're going to do, is we're going to go ahead and classify it as an ID because it does fit that rather cleanly. Okay, so we're serializing it so we can keep track of this. So sum square is an ID. So the problem is now we can accept ID followed by an assign followed by an expression. But in order for something to be an expression, going back to our rules, an expression is defined to be a term. What's a term? A term is defined to be a factor. What's a factor? Well, a factor is defined to be an ID. Oh, so there's a possible path right there to expression, which is what we tried to build our tree to say. Hey, if ID can be classified as a factor, then classified as a term, and then classified as an expression, we can accept that. And it does. It meets that criteria. But there's more, right? Because it's followed by div. So div is a reserved word. Sorry, I got ahead of myself. A div is a reserved word, okay? And it has a special function operation that it's going to perform. So where can we have an ID followed by a div? Well, we only saw that in one place, right? An ID followed by a div, well, an ID can be a factor followed by a div can be a term. So if we have a term, which we had classified, it needs to be followed by a factor, which needs to be either an ID, an integer, or a parenthetical expression. Well, in this case here, we have 100, which is an integer. So integer then gets classified as a factor. And then we saw with term could be a factor followed by a div followed by a factor. And a term could still be classified as an expression. So now we have sum squared div 100. Any questions so far with this? By the way, I did see these other questions up here. We will address them, but I want to stay focused on this topic here. And then we'll come back and we'll be glad to address those questions and address those at the time. So any questions about how this is going so far? Because this is going to be complicated a little bit more when we start doing our next evaluation. Okay, so we think we can, term refers to any directive. No, we go back to our rules for term. Term is defined to be a factor, or a factor followed by a multiply type, followed by a factor, or a factor followed by, that was classified as a term, followed by a div, followed by a factor. So those are the only organizational constructs that we can classify further as a term. Yeah, div was, since we used the div three-letter combination to be the same thing as that forward hash instead of the forward hash, the multiply, the asterisk we take as the multiply, we can do that. But Pascal uses that three char combination to define the division function. Okay. So we see that. Any other questions on how we got to here? Okay. So then we have this. So the next pairwise function will be the subtraction sign, and the subtraction sign is going to have another sequence of chars, which means it's going to be another ID, another variable, right? So we're going to need to find something that an expression can take and evaluate as a term, followed by a minus, followed by something else. So it turns out expressions, right, can be a term by itself, which we already saw, but it could also be an expression followed by a minus, followed by a term. And a term can be a factor can be an ID or an integer, and so mean can be an ID. Mean will be an ID, which means mean can be an ID, which gets classified as a factor, which then allows term to then say term followed by a factor can be classified as a term, and we could then say an expression followed by a minus followed by a term will allow us to be able to accept that ID. And that's what we see here, where we have term followed by the minus followed by another term. And we can accept that. So we're here. But now we still have this multiply and another ID, mean. Okay, we saw this exact same thing over on the left-hand side of this tree when we were doing the div here. So we had a term, we still do have a term here. So we have a term, which means that we can accept a factor, which can be an ID. But let's look and see what happens, because right now we think we've classified mean as a term. So let's go back here and say mean is a term, right? Because mean was an ID, which we classified as a factor, which was accepted and classified as a term. So what we're going to do now is we're going to take that multiply mean, right? Mean, the second mean could now be an ID classified as a factor. And now we have the term followed by a multiply followed by a factor will accept that second mean. So we have this first one, and now we have the multiply factor ID, which allows us to accept the second mean. So now we've accepted this whole statement here. But let's look at what's happening, right? Because we said that this particular grammar, those in particular, those two rules specified how the order of precedence would be performed. So Let left to right, leftmost derivation says, we had variance, which is an ID, followed by an assign, followed by an expression. The expression must be a term. The term must be a factor, some square. Then do the div with the integer 100. The results of this then come up to the first part of this expression. So that's this whole part here. We did the division first, followed by a minus, followed by a term. Well, the term must be a factor, which was the first mean, followed by the multiply, followed by the second factor, which was the second mean. Results of that is then brought up here, and then we do this evaluation. Then that comes up here to assign, which can then further complete this operation here by taking the results of that arithmetic expression performed in that specific order and assigning those results to variance, thereby ensuring that the div was performed first, left to right, the multiply was performed second, left to right, the subtraction was performed third, left to right, and then the assignment was performed fourth, left to right. Do you have any questions about how we did that? This is very important because this sequence that we walked through was very specific and very deliberate, because that is how we're going to build the compiler to do this particular work, which is then going to enforce this order of precedence by doing things in exactly this order. So yes, that's why we're using the tree, because we're going to force it to do it, well, sort of level by level, right? In the case of variance, we stopped at this level because it was ID followed by the assignment followed by the right-hand side, which we could not evaluate until we've gone all the way down to the bottom of the tree and came back up to this level. Now, if there was something above here, we could not perform that operation until this had been fully evaluated. So yeah, we're going to go down deepest, left to right. We're going to go down the deepest levels and come all the way back up, level by level. Excellent. Okay. Okay. So in the semantical phase, now we're going to go, if you think you've got a good grasp on that, we can go ahead and introduce this topic, because I'm looking at these questions here that we're deferring for the moment and starting to get a little concerned about making sure we have time to cover everything and make sure you're not too stressed out. So if you are comfortable with doing that LL grammar, the top down parser, we can certainly go on. We've got plenty of time here. And I'm going to start first off by going back up here saying, okay, we have now just finished the syntactical phase of our compiler. We've done the lexical analysis phase. We generated the tokens. We've now just done the syntactical phase, looking at two different approaches, bottom up versus top down, left to right versus left to right, rightmost derivation versus left to right, leftmost derivation, and stacks versus trees. And the results of that, of course, we now have all of those tokens now classified according to those grammar rules using either parsing trees or stacks. We've got them organized. Okay, so then the next phase of our compiler is going to do the semantical analysis of the compiler. In other words, it's looking to determine the meaning behind how is this program constructed, and how are we going to generate machine instructions based upon how it was constructed, the semantics or the reason behind this organizational structure here. That's what we're looking at here. The results of this is that we are going to generate this what we refer to as intermediate code, which is basically the program listing file that we saw in earlier chapters. It won't be complete, but it will be nearly so. It'll have the instructions all assembled. It'll have addresses assigned. It'll have memory addresses, of course, calculated, because that's what we're doing with the memory addresses. All of that will be done. It's just that we won't be completed just yet. So a lot of work to do here in the semantical analysis phase. All right. Sometimes referred to as the central phase of the compiler. It's going to do the insertion of the implicit specifications. So if we allowed implicit typing, if we allowed it that type of structure, I believe we gave the example in Fortran already. So drawn on that, we would then enforce those rules at this phase of the compiler. We'll also do macro expansions, which we spent a whole chapter looking at in this phase of the compiler. We will be looking for those directives, those assembler directives that we were talking about, other compile time operations. We'll be doing some error detection at this phase, looking for some things that we know can cause errors, and then halts if that were the case. And we'll be updating our symbol tables, and then the big clean step in this phase of the compiler is to transform these expressions into actual instructions. To do that, we're going to use these quads or quadruples to do this transformation. So those of you who are familiar with, and actually all of you should be at least familiar with functional programming, you're going to see that the quads are essentially performing functional programming on these trees or stacks that we have constructed in the earlier phases of the compiler. And we're going to do this in single function order, just like functional programming is going to do. So those of you who really enjoy functional programming, you're going to really like this part. Okay, because that's what we're talking about with the quads. The results of this work is that we will generate that immediate code like I talked about. And further, we'll go ahead and generate a program listing with some of these additional details after doing the symbol table maintenance and some other updates on some of the other data structures. That's the job of this phase of the compiler. All right, so implicit data types. All right, so if your language does support implicit data typing, this is where we are going to do it. And I gave an example earlier, but it's probably a while back, so it's worth repeating here that in some languages, Fortran is the most common, but it's not the only language that allows for implicit data typing. Certainly some other types which have a little bit more complicated rules, like Python has implicit data typing as well. There's a little bit more advanced, a little bit more structured than Fortran, actually less structured than Fortran, so you have to be very careful with this. But Fortran is very clear. Fortran, any ID whose name begins with these letters is going to default to an integer type. All others will be defaulting to a real type. Now it's kind of weird because you can actually override the default type and create a real type with a name that starts with like L in Fortran, but that's one of those things where you'd be really upsetting a whole lot of your team if you start doing that, because everybody working in Fortran, if they see a symbol, a variable name, an ID name that starts with one of these letters, they're going to just say, oh, that's an integer type. Nobody would really change that to a real, would they? Yeah. So keep that in mind. It can be done, but good practice says you don't. Okay. All the other types are reals. Also in Fortran, you don't actually have to declare I. If you want to just go ahead and use it like in a loop, You can just start using it in a loop and the compiler will figure that out for you. And it'll figure it out obviously as an integer. Another kind of interesting one is the symbol ID name average. If you create a symbol variable name average, it's just going to default to real. Of course, it starts with an A, so you would expect it to be defaulted to a real anyway, but it's kind of interesting. All right, let's talk about error detection then. And then again, back on implicit data typing, there are other languages that do support implicit data types. Python is one of those. It will determine what type to set it to depending upon its usage. So it's not going to be really clean and straightforward to implement like this, but it's still, there is a good way to do, when I say a good way, there is a very deterministic way to determine what the type of a variable is in Python. You're just doing a little bit more work in this, and specifically this phase of the compiler, to be able to determine what type that particular symbol name should be. So for error detection, then what you need to be able to do is be able to do different kinds of error detection in the compiler. Now, obviously in the syntactical phase and semantical phase, you are doing some error detection, right? If something cannot be classified by one of the rules that you specified, then that is an error. You should not go on. You should never get to this phase of the compiler if the syntactical or the semantical phase of the compiler had not been able to detect and classify some input as using one of its rules. Okay, so that's assuming that's been done up front. There's going to be some other errors that we're going to be doing down here in the semantical phase. Now, at this point, it's probably worth mentioning, and I think I did mention it once before, but we do need to be sure that everyone's on board right now with this, and that is all errors can be classified into one of two categories, either a recoverable error or a non-recoverable error. Essentially, a recoverable error are those that are you can live with. It's the type of thing where if you aren't sure that something should be an integer or a real, you could probably figure that out later on and catch it before things get too horrible and try to correct the error. Okay, so that would be an example of a recoverable error. However, there are some cases where you just can't proceed. Just like in the earlier, just like what I was just talking about, if you do not have a rule that can detect and classify some input or a sequence of inputs, then you can't make sense out of this program. You've just got to stop. You can't start guessing at what the programmer was trying to do, even if it's like a typo. Likewise, if you're at the point where you're generating memory addresses or you're trying to do some other rules that we haven't talked about yet in this phase of the compiler, and you can't figure it out, then you need to also halt at this point. So sometimes you'll hear some of the classes here that you've either taken or you will be taking talk about the halting problem. And you heard about this when you were doing your algorithms analysis class, right? When you talked about, NP complete types of problems and stuff like that. And some NP complete problems include those that are trying to determine halting problems in non-deterministic ways. And that is an example of a halting problem, but the halting problem is classically used here in the compilers, because if we're creating rules and we're generating and we're scanning input and applying these rules, and we end up in a situation at the end of scanning the entire input that we have not determined a halting point in this code, then we have a non-deterministic program and we need to halt at that point and flag this as an error. Now, sometimes instead of saying recoverable and non-recoverable errors, some programs, some compilers will use things like warnings and faults. Okay, whereas a warning is a cautionary type of thing, it's recoverable, you can go ahead and live with it, but you probably should clean it up. And you've probably seen lots of those as you were compiling your projects, not in this class, but other classes as well. And then you've seen faults occur, which immediately cause the program to halt, the compiler that is to halt, and you wouldn't be able to make progress. You wouldn't be able to complete compilation of your code because it came into a situation where it could not classify the input in a predictable, deterministic manner, and therefore had to just halt at that point, throwing a fault or an error, in that case, stopping. Okay, so that's, you've heard some of those terms used. That's what they're really talking about. They're really talking about those error conditions that are recoverable and non-recoverable. Okay, so in our compilers, in the earlier phases, we should be doing some error detection. And as you just heard in this phase, in the semantical phase, we're going to have some more complex error detection that we need to be watching for and testing for and building into the compiler in order for us to have a compiler that's going to generate code that can execute without crashing, because that's what we need to be doing with the compilers, is building them such that based upon these grammar rules that specify this language, and the programmer that's then writing code based upon those rules and the requirements that they have for this program, being able to write code correctly and without fat finger errors and things like that, being able to compile a object file, that an executable object file that can run correctly without crashing, because crashing is bad. And we don't, there's things that we can look for to prevent that from happening in the compiler itself. And this phase here is where we're going to build a lot of that complexity. All right, the other thing we talked about, macro expansions. It's kind of a reminder that some languages don't support macros. I think we talked about that when we were in chapter 4. So that's true. Some don't, in which case this phase of the compiler is not going to do a whole lot for macro expansion, like nothing. But some of them will allow us to be able to do macro expansions, in which case we're going to need to build those rules of macro expansion here in this phase of the compiler. So for example, in the C language, C++ language, you can do type definitions, right? Type def struct is the example here, where we said, oh, we have this struct that we're going to do a type def on called, and we're going to have two components to it, a real type A and a real type B. And we're going to name this specific instance of this struct. We're going to instantiate one right here called complex. Okay, so we defined this type def complex, and that allows us then to, I'm sorry, it's expansion there, but we're allow us to do this naming for this definition here, complex, and then we can instantiate, as you see in this next example here, instantiate two instances of it. One is comp, which is going to be a single instance of a complex type with a real A and a real B as members, and then an array of these complex types, CList, an array size of 10, each one having an A and a B, both are type real. Okay, so what that means then is in the macro expansion, because that's what this type defing is a macro, is the compiler's macro expansion built-in capability. If we invoke that as programmers, then in this phase of the compiler, when it sees that type def, it's going to say, I need to go ahead and expand this. So it knows then everything it needs to know here in these two statements to be able to build comp and CList as a single instance of two entities, or an array of 10, each of those 10 individuals having two entities within it. And it would know how to generate addresses to each one. It would know the sizing requirements for every A and B in there, and every instance one of comp, and all 10 instances of CList. So you can get to any one of those members, A and B, from any one of those actual instances, comp or CList at a specific indexed location. Make sense? Of course, this is just one example. There's lots and lots of macro expansions that languages can be supported. And that's the work that needs to be done at this phase of the compiler. So already you can start to see that defining a language in this phase of the compiler is very different than it was in the semantical and syntactical phase, where we had these grammar rules that very clearly specified what these rules are, and we can accept something or not accept something. Here, we're going to have to build macros, just like we saw in chapter 4. We have to build macros that, and a macro expansion capability that can then create the actual code to go in place of these instances of these macro names here to be able to generate something that the later part of this semantical phase of the compiler can then expand into machine instructions. Copy that. I'll take that as a yes. Okay, then in addition to the macro expansions, there's the operation, the compile time operations are directive, assembler directives or compiler directives that we can build into the languages. And here's some classic C and C++ directives, right? And we talked about the include directive for C. That's one of the things I wanted you to use in your assignments here, so you can use some of these other header files so that you can then tell the compiler when you go to compile the code to use those object files instead of you having to then take and build each one of those functions yourselves and then verify and validate it and all that stuff, right? So we can do those pound includes. Well, we need the header files to help this phase of the compiler understand, the previous two phases of the compiler understand and recognize those rules for accepting those functions that you decided to use in your program from the object file math.o or math.lo or math.so using the header specification that was in math.h for those specific functions. That way the compiler can recognize them. Other things we can do too is we know C doesn't have things called strings, so we can make something convenient for ourselves. Say, okay, instead of saying char pointer all over the place, maybe I want to say string and make it look like some more modern compiler. We can do that, or language, we can do that. Same thing with Booleans, we can make those shorts. Here's a good one though. I really like this one. If you have not used these next four, then I strongly encourage you to look into this further and experiment further with your next project, or even go back and take a look at some simple places inside of this project where you can insert these and see if it makes sense. Where pound define, what it does is it just says you give it some name and a value. So in this case here, we can pound define says I want to create a name, in this case debug, and set it to some value. Define the name and set it to some value. And typically with a statement like this, debug can be 1 or 0. And that way we can test, and we can do a test if defined. We can also do if not defined, if indef, if defined debug, and then you can put in your print statements and then do an end if at the end of your print statements. And then you can compile your project simply by setting this to 1 or changing it to 0 for the final delivery, in which case it'll strip out all of those print statements or other debug statements that you put in between define debug 1 and end if. So John made a comment here where he's defined success and failure as 0 and 1. That's fantastic. This is a fantastic tool. The other thing, as an example here where we define Boolean as short, is also important because when you start taking your source code and you're porting it across different systems, it could be either different versions of the same operating system, different hardware with the same operating system on top of it, or you could be bringing it up to newer operating systems or even different versions of the operating system, in which case in some cases, Boolean, you might want to define it as a short, but in some other operating systems, you might want to define it as maybe a U underscore short. You can change once what that definition of a Boolean function is, and the compiler will then, in this phase of the compiler, will then substitute every place that you have Boolean for short, or for U short, or for U underscore short, whatever it is you want it to be. So you might use it 10,001 times in your program, and instead of making 10,001 search and replaces, you just simply use bool everywhere that you want to have that short function, that short integer type, and all you have to do is just change it once here, and the compiler will go and substitute it everywhere you use it, all 10,001 locations in your source code that you used it. Very powerful capability, very simple construct. And it's a very simple thing for the assembler to, for the compiler to do in this phase of the compiler operation, where this operation, this compile time operation in this case here, is simply doing a one-for-one substitution. And it's easy for the code to do that. Okay, so I'm kind of mixing two things up in this one slide here. One is that from the compiler perspective, what does it do when it encounters one of these things? Well, it's simply, in the case of defines, in the case of these defines here, it's creating a table entry saying, hey, we've created this name here, and it has this value here. So anywhere that the programmer then uses this, it's then going to do a substitution with this. Every time the compiler encounters where the programmer used this, it will substitute it with this. And then the conditional logic, it'll just follow the conditional logic. When it encounters this, if define debug, then it knows that you are supposed to do this work in between if define and the else, or if define else indif, or if define indif. It's going to do that work using simple logic analysis here. From writing code perspectives, because that's one of the reasons why we have the operating systems class and the systems programming classes for you. Is some of you are going to go off and you're going to write system code. Some of you are going to go off and work on systems tools. Some of you are going to work on embedded systems. Some of you are going to work at application level. Maybe once in a while you might dabble at these other levels, or maybe you never do. But even in those later cases, knowing how these kinds of tools work, how they're actually implemented in the compilers and the assemblers, is going to help you write better code and take advantage of these tools, because you know how they work and you know how you can take advantage of them, and you can actually write fewer instructions that have to execute at runtime, or write smaller programs that gets smaller at compile time, by being able to take advantage of these kinds of built-in tools that are instructions, directives to the compilers and to the assemblers to do work at compile time, and not do that same work repetitively at runtime. Because runtime is more costly when you're doing that code execution over and over and over, which is why you're usually writing code, is you want it to run many times by many users. In the compile time, yeah, you're going to do some compiles. You're going to do a few compiles, hopefully relative to the numbers of times that your program is running, but not always. If you're writing analytical code, if you're writing some code to do some analytical work, you're probably going to do as many compiles as runs, or maybe you'll do more compiles than you do actual runtime execution of your code. So the difference in the number of times you compile the project versus the number of times that you run the executable code is going to pretty much persuade you which one of these ways you want to go. Do you want to spend more time looking at how to use tools like this, or do you want to spend more time just writing flat out code and letting it run? Okay, but understanding how these tools work give you the kind of tools that you need to be able to make that kind of decision efficiently with. And that's what we're about. We're about optimization, and we're about efficiency. Optimization at runtime, hopefully, efficiency everywhere. So before I go on, any other questions? All right. At this point here, I think what I want to do is back up and let's address some of these other questions that are going on. I think I want to leave the rest of this discussion for a new clean lecture because we're going to need more than 15 minutes to go through that. And so I want to leave that nice and clean. All right, so I think I'm going to start. Well, let's take this next to bottom one first. How will mini exam 2 be counted towards final grade? It is going to be an additional 15 points on, I haven't actually decided, it's 10, 12, or 15 points onto the total amount of points that you need to earn a grade. Okay, so that's the way I'm doing it. Now, one of the things I am thinking about is whether I take if I do 10 points, I'm probably going to take 10 points off of the final, and we're going to do that as this mini exam. If I decide to go with 15 points, it would be in addition to all of the exam points and assignment points. So that's why I'm deciding, and I will let you know Wednesday for sure how I'm going to do that. But the bottom line is that mini exam 2 is not extra credit. It's going to be part of the points required to earn a grade in the class. And the mini exam will be next Monday. Trying to get back into this other tool. I have so many things open. There we go. All right, so here we are. So next Monday is the 27th. So yes, it'll be on Monday, the 27th. And again, it's going to be similar to question number 6 on exam number 1, which means basically you need to know how to assemble instructions, calculate addresses, and when you're calculating addresses, being able to accommodate those assembler directives that might cause you to jump over memory addresses or preset memory address locations to certain values, i.e. the reserved words and the bytes and the words and all those things. Okay, so you need to know how to do that. And that's why I'm going back and revisiting that question, because it's an important concept to take away from this particular class. Okay, scrolling back up here a little bit, with assignment 3 due on the 6th and our final on the 8th, when should we feasibly expect the program to be completed by? Yeah, so here's the deal with assignment number 3. Some of you are going to get it and you're going to be done within a day. Some of you are going to struggle a little bit with it and you're going to take several days to get through it. Some of you might be prioritizing other things that you're doing and you might want to take the whole time. The reality is it should only take you a day to do this particular exam, although I can understand some people saying I'm struggling with it. I just need to need to get some rest and come back and look at it a second day, although the second day might be on the third day, whatever. So I give you a few days to do this. However, if you're really struggling with it, I don't want to cut you off too early, and I want you to be able to finish this assignment nice and cleanly. It really should not take too long to do. And so therefore, most of your study time should be, most of that time that you even have for this assignment, you should be able to focus on preparing for exam number 3 at the same time. Should not be a problem. And yes, I do understand there's lots of things going on in people's lives right now. That's why I'm trying to get as much done up front as we can. And also, and this leads into the previous question here, you saw the announcement from the university giving you options to go credit, no credit instead of letter grade. And that's something that may or may not help you depending upon how you feel you are doing here. And part of that is I'm going to get these gradings done for this assignment number 2 pretty quickly so you can get to see what that looks like. And the other part of that question is what will be the basis for passing your class with a credit or failing your class with a no credit? How will you overall handle the grading and accommodate students who choose that option? So credit, no credit, I'm still looking at in a little bit more detail. At the very basic level, that means passing or not passing. Passing means you're getting a D or above. Not passing means you are doing D minus or below. So that's the basic fundamental level. And we have in the syllabus how to assess that particular component. I'm looking to see if that still makes sense in light of this decision. I think it does, but I will let you know on Wednesday for sure if I'm going to deviate from that or propose deviating that or not. You need a C for credit, D for no credit. If that's what the department is saying, I'm going to go with that. That's one of the things I was going back to check on is what their current definitions are. There had been other definitions previously. In our conversation at the department level earlier, that had not been promulgated just yet. So once they do, I'm going to be conforming to departmental standards and going with basically that. But again, I'm going to look at my material specific to this course that I need you to understand to say this is a passing grade. And that's what I'm going to make sure matches with whatever the criteria the department says as far as C or D++ or D, as far as passing, non-pass. So I will promulgate that as soon as we define that. And my goal is to have that defined by the time we meet on Wednesday. And Trevor asked about an answer key for question 6. The problem was, I toyed with that. I started to say, yeah, sure, let's do that. But then I go back and I looked at the errors on the papers, and by far and large, they were very fundamental errors in being able to calculate addresses correctly or assemble instructions correctly. And so what I would like to do instead of just saying, yeah, here's the whole key for the whole thing, is go back and do a refresher on how to assemble instructions and how to calculate addresses and walk through those using parts of question 6 to come up with some of the answers and not necessarily the entire answer. And so I see a request for assignment number 3 being partners instead of individuals. Again, that's a tough one. I prefer having it individual because if you partner up, that doesn't tell me that you do understand the YAC specification or the LEX specification and being able to generate something pretty simple. So that's the point that I'm still considering, and I'm leaning towards individual for that very reason. If I make it a partner assignment, then teams of 2 can partner up, and half the team can think they conceptually get the idea, and probably conceptually they do, but they still could not execute a simple parser. which you should be able to do graduating from this class here. As long as format 2. Format 2 and format 1, that's another favorite. Sure, there'll be a format 2 thrown in there. There will probably be a format 1, but you really need to be focusing on the formats 3 and 4. And again, I'm not going to go over the entirety of problem number 6 from the exam, but we are going to go through the key components of it such that you should be able to take away from that and assemble any instruction or any series of instructions. Great question, Trevor. This is a good one. So yeah, I already hinted that assignment number 3 is going to be Lex and Yak. I'll post it on Wednesday. But if you want to start taking a look at that, go ahead and open up those slides that I've already posted, because what you're going to do is you're going to build a simple parser using either Lex and Yak, but I would recommend Flex and Bison instead, that can then parse a simple grammar and be able to generate executable with it. Sure, not a problem. That's what we're here, is trying to make sure we understand, because I understand it's hard when you're looking at this conceptually and you're sitting here staring at this one screen that doesn't even apply to the questions you're asking about. And this is a little bit more challenging, though we do have, oops, I didn't mean to do that. I took away the chat window. Come back, chat. There's chat window. Let's come back to this window. No, I don't want to do that yet. There we go. That's what I was trying to do. Because if you go over to the class page on Blackboard, you go into course documents, and if this thing wakes up and listens to me, there we go. You go into the lecture slides, and you'll see in here, boy, this is really slow tonight. You'll see here we already have the introductory slides and walking us through Lex and Yak that we're going to cover, but you can go ahead and start reading through that, or you can go and start looking through some of the readings as well. And I think I even included, no, I didn't. Thought somewhere else I included some sample files. Oh, yes, the Lex-Yak reference. This is a good one here. Okay, so I would also recommend going to this source here and taking advantage of that, in addition to the slides that I posted in the lecture slides. So Lex and Yak are system tools that are usually built by the operating systems people that do the lexical phase analysis and the syntactical phase analysis of, and sometimes the syntactical and semantical phase analysis built into Lex and Yak, Lex being the lexical analysis tools. So you can build your lexers using Lex or Flex that can implement those grammar rules that you specify for the parsing. And then you can build all of your semantical rules into a specification, as well as the rules for what a C compiler does, and feed that into Yak or Bison, and it will generate it'll compile some source code for you and generate some object files. So it's pretty powerful tools, and what that does is that it allows you as compiler developers to, instead of rewriting that same code for every hardware operating system combination allows the operating system people themselves to say, hey, I'm writing this for this version of our operating system, and we're going to build our rules for being able to do things like macro processing, error detection, and these other things that we haven't talked about yet. They'll have all those rules built into the rules for the C runtime, which we haven't talked about yet. So we're kind of getting ahead of ourselves, but since you asked about being able to do some read aheads, I'm pointing those out to you. Otherwise, if it's confusing you, just stand back and we're going to talk about those. We're going to walk through those. So the answer for the question about the assignment points is yes. Assignment 1 is 26 points. Assignment 3 is 26. And I intentionally made assignment 2 more points, the full 100 points, when I knew that we were having issues with the environment around us, and that you were going to be able to work more efficiently on project assignments than working through some of these more theoretical problems that are harder to work through using these remote tools than the practical side of the assignments. So I was trying to tip things in your favor a little bit by giving you additional points for assignment 2. And as far as office hours, sure, we can stay here as long as you would like. As long as you have questions, I am here. And to answer Austin's question, yes, by and large, Flex is better than Lex, and Bison is better to use than Yak. And if you haven't heard of the O'Reilly Nutshell series of books, they have them for Lex and Flex and for Bison and Yak. And they're very straight reading, easy to comprehend, great examples, really easy to follow books to help you understand any of these tools that, and way beyond these. They have hundreds of these things, one for every kind of tool, every kind of compiler, every kind of system tool or editors, lots of different capabilities. There's a nutshell book in the O'Reilly series for it. And they each have their own animal on each page or each cover, kind of unique for each specific solution. And so that's a good question about the time of the mini exam. What I will do is I will start it up officially at the end of lecture, and it'll be a timed exam, and I'll leave it open for probably 12 hours. I might leave it open for 24, but it'll be a timed exam. Yeah, the mini exam, I held that one open for 3 days because it was the first time people were using it, and I wanted people to be able to, work through some of your connectivity issues, some first time connectivity issues, and being able to get some familiarity with the tool. So and some of you needed multiple attempts, and that's all fine. That was the whole purpose of the mini exam, was to just kind of get everybody involved with using this whole new environment. I wanted to give you maximum flexibility so that you can be more focused on learning how to use the tools and not so much about points. For the mini exam, however, it's going to be the opposite. Now you've got some experience with it, and now I need to focus on, okay, you now know how to use the tools, and now we need to focus on how long it should take you to really answer this question and be able to time it according to that. That way I'm not just leaving it open-ended, so that you can go off and research it on your own, come back with some answers that are not fair. I haven't decided on exactly how much length of time yet it's going to take. We working. I'm going to finish hand building the question myself. Once I finish hand building the question and hand answering it, I will then have a good idea of how long it should take you as a student to be able to answer it. Oh, it'll be way less than an hour. I don't know the exact time yet. I've got to determine what that is, and then I will let you know. I agree with you, John. I hope everybody else is staying safe, healthy, and sane, and make sure that there's lots of good resources out there to help you manage your time while you're in this environment, and hopefully you're heeding those things. You're spending some time doing different kinds of activities. You're not just doing one thing over and over and over again, and or staying disconnected. Hopefully you're reaching out to other people and staying connected with others. Make there's this really novel tool called the telephone or cell phone, and you can call people with it and actually talk to human voices instead of texting, instead of zooming, instead of um, facebooking, instead of twittering and all these other tools out there. You can actually talk to live human voices. I strongly recommend it. You should try that. It's a good thing. I know a number of you probably have, and I'm being somewhat facetious here, but I'm also being serious. If you're one of those who's like, yeah, I like being behind a keyboard and the screen and I'm good there, uh, that's okay, particularly the screen part. You got that going. That's good. If you're doing live mic and live screening, that's good. But if not, get on the phone with somebody and talk with real human people and do that on occasion. That helps. Thanks. Okay, so for those of you who would like to have um, individual office hours, what I think we could do, because I haven't played with this part of the tool yet, I think probably the best thing to do would be to terminate this session and then send me an email, and then we can open up a session to you. Okay. So let's do that then. I'll go ahead and break this off. Wish everybody well. See you virtually on Wednesday night. And for those of you who would like some, again, office hours here, send me a quick email, contact info, and we will get with you that way. Thank you.